Hello everyone, and welcome to this talk on QEMU and NVMe Emulation and what's new and some of the features that we've gotten over the last year. This talk is presented by myself and Pat McCarr and Naveen. So first we'll go through a little bit about emulated NVMe emulation in general. Then we'll talk about the new features. Naveen and Pat McCarr will cover that, and then we'll round up in the end. So there's actually several emulated and virtual NVMe controllers available today. There's the QEMU emulated PCIe-based NVMe controller. That's the topic of this talk. Then SPDK actually has a virtual controller, which is intended primarily for fabrics. But in this case, I think you should check out the exciting work that the VFIO user guys are doing with making this available to QEMU. The kernel actually also has a virtual emulated controller in form of the NVMe target that's used for fabrics. So feature and compliance wise, QEMU is the most feature complete. It's not intended for high performance, but compliance, correctness, and to a lesser degree, as we should see, feature completeness are the primary goals or concerns for this device. I think Keith put it very well when he said that performance improvements are always welcome, as long as we don't harm protocol correctness or maintainability of the device. So this is about feature completeness. So to not fake a feature. Well, the point is that we're not trying to bloat the device. We try to rely on system support and QEMU support whenever possible. And as we shall see, some features that are useful for compliance testing may not be appropriate for upstream QEMU. An example of this is the write uncorrectable command, which requires a substantial amount of in-device tracking of the uncorrectable status in form of bitmaps or something like that. And we don't have any QEMU support underlying this that can do this through the QEMU block layer. So this is not intended for upstream, and generally it's not supposed to be merged upstream. Now, there are notable exceptions to this when we have to do like extensive faking, and this is an example of this is the zoned namespace supports, because zones in this case are faked and tracked exclusively by the device, but the value of these features is very high, and it's very clear that it's a high value for this feature. The same is true for end-to-end data protection, which is also pretty compute heavy in device, but the value of being able to test this and work with this is pretty high. Now, so some of the features that will be described in this talk, they are not upstream, but they are available as patches on GitHub OpenMPDK that you can see below. So new features. So one of the new features that we got is universal dual support. And dual support is an error recovery feature of NVMe that allows the host to detect blocks that are unwritten or considered unwritten or deallocated by the device. Now, it's a special recovery feature that you set using the set features command, and it will give you an error if you try to read one of these blocks. So in NVMe logical blocks, they can be marked deallocated. Initially, in most cases, they will be deallocated, but they can also explicitly be marked deallocated after being written to. You can do this through the write zeros command, which always guarantees that zeros will be read back, but it might also deallocate the block. The dataset management doesn't necessarily zero anything, and it doesn't even necessarily deallocate anything because it's an advisory command, and the device may choose to take no action whatsoever, but it can also be used to deallocate blocks in most cases. So the QEMU block layer provides something called block status information through a set of block status flags. So you can use the QEMU block layer to get these flags for a range of LBAs. And if you issue the discard of the write zeros command, the p discard or the p write zeros in QEMU, they may explicitly mark these blocks as zero. So what we do is that we can add the BDRV block zero flag. The BDRV block zero flag tells us something about that it's guaranteed that we will be reading zeros back from this block. So there are actually multiple factors that affect when blocks are assigned this flag as a result of write zeros. So it depends on the underlying file system logical block size. It depends on the format of the underlying device, RAW, QCOW, or whatever. And the point is here is that raw relies on actual file system hole punching, and QCOW relies on simply tracking the allocation status of blocks in internal metadata. And there's also the device discard parameter, but that doesn't matter for write zeros. So you can see this table here, because the normal, assuming a file system block size of 4 kilobyte, we can only get this flag set in a granularity of 4 kilobytes and at the alignment of 4 kilobytes. This means that for raw commands when issuing, for raw format when issuing a write zeros, we'll get this flag set for 4 kilobyte and say 64 kilobyte, whatever, it's a granularity of 4 kilobytes. But because QCOW manages the allocation in clusters of 64 kilobytes, then you cannot get the zero flag set by just writing zeros to one logical block of 4 kilobyte. You need to write zeros of full cluster before this flag is actually set. But this is still good enough because the write zeros command says that it may deallocate the block. It doesn't have to. So similar for DSM, which we have not implemented with write zeros, but with the discard. So it is advisory, like in the spec. And as we can see, then this is where the discard parameter on the block device matters. So if the discard parameter is set to ignore, then the discard functionality, the discard will simply never reach the block layer or go through the block layer to the underlying device. But again, this also works on the granularity of the underlying file system. So as you can see, the preferable setup for this is using a raw format and using a logical block size that is set to the native logical block size of the underlying file system or the block device if we're using a pass-through block device. So we also got various namespace types, and we got support for the zoned namespace type. And this is through work of Nicholas, who added namespace type support, and Dimitri added support for zoned namespaces, where we have the emulated support for zones and zone append. Now, this is not the topic of this talk. There were 2 talks last year at SDC by Dimitri and myself, and I recommend you to go and look at those if you want to see more about the implementation of zoned namespaces. So I want to talk a little bit about namespace sharing, because a big feature that we got this year is support from NVMe subsystems. And a shared namespace is basically a namespace that can be attached to controllers and allows you to have 2 paths to that controller. And it's very useful for testing advanced drivers and multipath I/O in general. So the way we did it is that we added a new subsystem device, which is implemented as a busless and unrooted device. We should see what that means. And we added a subsys link parameter on the controller to plumb it up to this namespace. There's actually 2 ways of doing this in QEMU. So you can use these unidirectional reference styles relationship that you do with these links, where you can reference another device. But you can also use these buses, and that's how namespaces works right now. So namespaces will attach to controllers through these buses, and buses the buses are part of the QEMU QDev API, and it offers a very strict relationship where you have a parent that can have a device can have multiple devices attached, but a device can only be attached to 1 bus at a time. So it offers a strict tree. So today it looks something like this. You have the main system bus, which has the PCI bus, and then you have the NVMe controller on that has the NVMe bus, and the namespace is attached to that. That's nice. So, but the problem is that you get this nice unrealization, which is nice, and it should be a good thing. It causes that when you hot plug the device, then will automatically remove the underlying namespace devices. So when you have the subsystem involved, you have this unrooted device that's anonymous and not rooted on the tree, but you have these references to it. The problem is that, as you can see, the namespace devices, they can only have 1 parent, and the parent is the controller. But even though they are visible to both controllers, the problem becomes that if you remove one of the devices, then the namespaces are still in NVMe terms attached to the other device. But the devices are automatically cleaned up, so they're gone. So the way we fixed this is that we added a new instance of the NVMe bus directly on the subsystem, and then the namespaces instead will attach to that bus on the subsystem. But the real fix here might be to rethink this model because something is wrong. And the point is that what if we actually subsystem namespaces were not modeled as devices? QEMU offers something else, which is called user creatable objects. And the point here is that the namespaces in the subsystem are not really devices. They don't expose virtual hardware, memory, or interrupts, or anything like that. Fundamentally, they're just concepts, but they happen to benefit from being individual objects or devices in QEMU. So I posted a pretty big patch for this called the Apocalypse, which basically is a big refactoring of this that takes the namespace and the subsystems and change them into user creatable objects. So the goal here is that it's introducing a new experimental control device, which support for these new objects, and introduces new experimental user creatable objects in the form of namespaces of two types, NVMe and the Zoned namespace, and a subsystem object. So it exploits the QEMU object pretty extensively by having an abstract object that implements the core namespace functionality, and then you have the NVMe that extends this, and then the Zoned namespaces extends the NVMe object because it's basically just an NVMe namespace with additional functionality. And we're keeping backward compatibility completely because we're reusing the same new object code for the devices. So of course, when this stabilizes, the goal is to deprecate the old devices. So there are some perks for this, that we can remove some of the deprecated functionality, which should have been deprecated long ago, and we can also fix some parameters that were defined in the wrong way and stuff like that. So basically what you do now instead is that you define an object as the subsystem, then you define your controllers, you add them to the subsystem explicitly, and then you add the namespaces, and you also explicitly add those to the controllers that you want them part of. But notice that the objects also have a subsystem link here, so they have a direct reference to the subsystem, and that's how the topology is set up. Okay, that's it.
Now we'll talk about the CMB and PMR enhancements, which has been added in QEMU as part of NVMe 1.4 feature enhancements. So NVMe 1.4 talks about some major enhancements related to CMB and PMR. So earlier in NVMe 1.3, so the guest driver needs to update the CMB and PMR addresses as part of the bar in the PCI config space. Whereas in NVMe 1.4, the spec says that we need to update it as part of the CMB MSC field, CMB MSC or PMR MSC field, which we will talk in detail a little while. Basically, this is to avoid DMA mesh routing from in case of a hypervisor or a VM setup. And QEMU has implemented this enhancement. And also the way it emulates the CMB and PMR region is by allocating a memory region in the host OS, in the QEMU host OS. And also along with this, QEMU has also handled some cases wherein the guest is not supposed to write into the CMB and PMR, and accordingly it will return error saying invalid use of CMB address. And the way users can specify the size parameter for CMB is in the launch command. So in the launch command, there's an option to specify the size of the CMB, and also users can specify the backend file for the PMR. So the reason why we have file is basically since PMR needs to be persistent, so it has to be present in a file. So that's the reason we ask the user to specify the file for PMR. So here I'll try to explain how the DMA mesh routing happens. So let's say we have a hypervisor and a VM. So now the hypervisor initiates a transaction with a memory mapped CMB address, and once it reaches the controller, so the controller knows that this is a CMB address, and it will translate it to CMB and it will do a read or write operation properly. So whereas once if the VM does a similar transaction with the CMB address, which is memory mapped on VM, and it reaches the controller, so the controller does not know that this particular address is whether it is CMB or not. So because of which the translation does not happen, and the controller might think that this particular address, it is present on the VM itself, and hence the misrouting happens. So this particular enhancement in 1.4 so helps in avoiding this DME misrouting. So now let's talk how the guest driver can configure these addresses. As I mentioned earlier, so there's a CMB MSC field, so which is part of 0x50 for CMB, and similarly we have a PMR MSC field as well. So under that we have one field called as CRE field, that is capability registers enable. So this will enable the CMB size and CMB location parameters. So by default, when the driver is loaded, so these parameters CMB and SZ and CMB location parameters are set to 0. So if the guest driver needs to know what is the CMB SZ and CMB location parameters, so it writes the CRE field as part of CMB MSC, and once it is written, the QEMU will populate these two values, that is CMB SZ and CMB location parameters. So after the CRA is configured, now the guest can write the CBA. So CBA is nothing but the controller base address, where the actual address of the CMB and PMR region will be configured. And along with that, this will also write the CME SC, that is nothing but the controller memory space enable. So this is to tell that the memory region for CMB or PMR has been enabled. So once the CBA is configured, so what the QEMU will do is it will check the validity of this address. So there are two major criteria. So one is that it must fall within a range, and also if it is a CMB address, it should not overlap with the PMR address, and if it's a PMR address, it should not overlap with the CMB address. So if these two criteria are met, then there's one more field called a CBAI, that is controller base address invalid. So if the criterias are met, then the CBAI field will be set to 0. Otherwise, it will be, if it is invalid, it will be set to 1. So this is how the addresses are configured as part of the NVMe 1.4 enhancements for CMB and PMR.
Hi, I will talk about namespace management feature. So we will start first by understanding about namespaces. A namespace is a quantity of non-volatile memory storage that may be formatted into logical blocks. So a namespace is a collection of logical blocks that can be accessed by the host software. There are many reasons why host software would want to break up an NVMe SSD into multiple namespaces. For logical isolation, security isolation, right protecting a namespace for recovery purpose, and so on. Namespace management provides an interface for the host to manage the multiple namespaces. That is, namespace creation and deletion can be done at runtime. So as spec, there can be various types of NSIDs. So first one is the allocated. So a namespace is in allocated state when it is created using namespace create command, and namespace will be in unallocated state when it is deleted using namespace delete command. Similarly, a namespace is in active state when it is attached to a controller using namespace attachment, and it will be in inactive state when detach command is received. So what is benefit of namespace creation at runtime? Following attributes can be modified. Logical block format such as data block size and metadata size can be changed. Here namespace size defines the total size of namespace in logical blocks. So each namespace can be uniquely configured. Each namespace will have their own metadata size, block data size, and their own protection capabilities. Host software can also determine whether this namespace will be shared across multiple controllers in the subsystem by providing NMIC field. Now we will see the design implementation on QEMU side. We can add any number of NVMe devices during launch time. If size of underlying block drive is non-zero, it means that namespace is allocated and it will be initialized properly. If size of block drive is 0, it means it is unallocated namespace. So at runtime, namespace creation will grab an unallocated namespace and initialize it properly with a certain size that host has specified. And we have added a new parameter tNVMe cap, which is necessary to make sure that total capacity of all the created namespaces should be less than T NVMe tag. To explain our approach, I took small NVMe subsystem model, which is containing one subsystem, two controller and namespaces. Here, subsystem ID is subsystem 0 and total capacity of subsystem is 8 GB. We can see there are two controller devices, controller device 1 and controller device 2. These are modeled as NVMe bus devices. The next level to controller are namespace devices. The namespaces are modeled as NVMe NS bus devices. So when we created ns1.img, we have given the size of 1 GB. And for ns2.img, we have given the size of 0 GB. So in this case, namespace 1 will be initialized properly, but namespace 2 will be added in a list of unallocated namespaces, and it will not be initialized. Let's say at runtime, namespace create command comes, device will check the list of unallocated namespaces, and namespace 2 will be initialized properly. And we use block truncate to change the block device size from 0 to namespace size provided by the host.
Let's now talk about the EDP feature, that is end-to-end data protection. So NVMe provides support for metadata for the logical blocks. So this metadata can be used to have data protection for the logical block. So also this metadata can be of varying length, so starting from 8 bytes to 128 bytes. And in this metadata, we can have the protection information restricted to 8 bytes. But as this is as per 104 specification, but in the upcoming specification, so we can have metadata, we can have the protection information even of more length. Also, the specification talks about different types of metadata. So one is diff, that is data integrity field, and the other is data integrity extension, that is DIX. So in diff, we can have the metadata in continuation with the logical block, whereas in data integrity extension, so it will be separate. So this is the logical representation of how diff and DIX looks like. So as you can see here, in case of diff, so the data and metadata are in continuation with each other, whereas in DIX, so we have data separate and the metadata separate. So also let's talk about what does this protection information actually contain. So as we mentioned earlier, the protection information consists of 8 bytes of data. So in this 8 bytes, it is divided into 3 main parts. So the first 2 bytes contain the guard tag, and the next 2 bytes contain the application tag, and the remaining 4 bytes is the reference tag. So the guard tag is nothing but the CRC calculation which is done over the LBA data. So this will help to know whether the logical block data was corrupted or not. And similarly, we have reference tag as well. So this reference tag will contains the logical block number of the data. So this will help to know whether there is any out of order data or not. So basically, to support this diff and DIX format and to store data, QEMU provides the block image files. So during the launch parameters, we can specify the file where we will store the data. Also, since diff is like storing the data in a contiguous manner, so one image file is sufficient to implement this. So but whereas in DIX it is separate, so we need to have one image file for the data and another image file for the metadata. So this is how the data is. This is how the diff and DIX is implemented in QEMU. And also currently QEMU has provided EDP support for various commands like write, read, compare, write zeros, copy, and verify commands. Yeah, so this is about EDP feature. Now let's talk about the endurance group feature. So this is the overview of how an endurance group looks like. So as you can see here, so there are multiple namespaces grouped into NVMe set, and different NVMe set comprises of endurance group. So similarly, we can have different endurance group as well. So the endurance group helps in better management of the SSD. So how it helps in better management of SSD is, so we can have a logical separation of different media units. So let's say if I have different NAND types, let's say I have SLC, TLC, and MLC NAND types. So I can associate the SLC based namespaces to one endurance group, a TLC based namespaces to another endurance group, and so on. So with this, we can better manage the SSDs, and also we can help in the improving the life of the SSD as well. So what QEMU has implemented is, it has implemented the endurance group log pages, endurance group aggregate log page, and the AR generation in case of critical warning. So since QEMU does not implement the NAND functionalities, so what we have done is, we have provided HMP command, so which is specific to QEMU, to generate a to trigger a critical warning and subsequently raise AR for that endurance group. So we will talk now how the HMP command is issued and how subsequently the AR is generated. So as you can see here, so we have a HMP terminal on the guest VM. So from the guest VM, we can issue HMP command to set the critical warning for that particular endurance group. So basically, this is the way to emulate the critical warning in case of QEMU. So once this command reaches the QEMU, so it can see for which endurance group the critical warning needs to be raised, and accordingly it will raise the AR for that particular endurance group, and it reaches the guest. Yeah. So this is how the endurance group is implemented in QEMU.
Now we will talk about reservation feature. Our NVMe reservation should be supported to address a requirement when multiple controllers need to access one shared namespace. So it force submit a command to the namespace in the presence of reservation and does not have sufficient rights. Then that command is aborted by the controller with the status of reservation conflict. So this is an example of dual port. Here, namespace B is shared and reservation commands can be issued on this particular namespace by the host. Different host identifier can be assigned to each controller using set feature command. There are four types of reservation commands. In register command, host can either register or register to replace a reservation key. So register command is a prerequisite for acquiring a reservation on a namespace. And we can say that registering a reservation key with a namespace creates an association between host and a namespace. In acquire command, registrant obtains reservation on that namespace, and only one reservation is allowed at a time on namespace. In release command, reservation follows the release of reservation, which is carried on namespace. And finally, a host may determine the current reservation status associated with the namespace by executing a reservation report command. This is the first command. It uses command equal 10 submission queue entry. We can issue this command from NVMe CLI in Linux, and after that, host will get registered to that particular namespace. Similarly, this command can be used to acquire the reservation. And reservation release command is used to release or free the reservation. And finally, reservation report command will return information about current reservations. So, while acquiring the reservation, host application will also specify the reservation type. If reservation type is exclusive access, in that case, only reservation holder can perform read and write operations. All other hosts which are registrant and non-registrant cannot access this particular namespace. Now, we will see one practical example that three hosts are available in the subsystem with different host identifiers. And now, let us say host A issues a register command with some key value, and host B also issues a register command with some other key value. So these commands will be successful from device side. And now host A wants to acquire a reservation, and reservation type is exclusive access registrant only. And this command will be successful also. Now host C wants to acquire a reservation on namespace and the reservation type is same. In this case, device will return an error, that is reservation conflict, because host T is not a registrant for that particular namespace. And we have seen that if reservation type is exclusive access registrant only, and in that case, the reservation holder as well as registrant can perform read and write operations on that namespace. So we can see that host A is a reservation holder, so it can issue a write command, and host B can also issue a successful read or write command. But let us say now host C wants to perform read or write operations. So we have seen that host C is not a registrant, so QEMU device will return an error, that is reservation conflict. After that, host A releases a reservation that particular namespace. And now host C wants to perform write operations. So in that case, write operation will be successful because reservation is not acquired by any of. If we talk about the implementation of reservation feature in QEMU device, then we are maintaining one map data structure, and each entry in this map will get modified for each reservation operations like register, release, acquire, and deploy. Also, as per spec, we have added condition in front of each IO command. We check whether host has sufficient permissions or not. If not, QEMU device will return reservation conflict error.
Now we'll be talking about one more feature, that is NVMe MI in QEMU. So here we have proposed and implemented a new module in QEMU, that is implementation of NVMe MI. As many of you might be aware that QEMU currently supports NVMe or PCI transport, but our implementation is to support NVMe MI over I2C, that is over sideband, not over the PCI. So this, to enable the testing of this QEMU MI interface, we have also implemented a plugin for MI in NVMe CLI. So even that has been released as an RFC. So how this will help is basically the QEMU implementation for NVMe MI will help in testing of various modules. Let's say it could be a test suite, let's say test case, or it could be platform. Let's say if you are developing an application to test your SSDs. So before the arrival of the actual device, you can test these modules over QEMU. So in this way, it will help developers, test for developers and platform developers to test their features and be ready to test when the actual device arrives. So currently, what we have done is we have implemented certain features. So certain features and commands like read NVMe MI data structures, get and set config. Certain configurations in get and set config, vpd read write, and certain admin commands. NVMe admin commands also has been implemented. So like under identify we have implemented CNS 0 and 1. So for get log page and get features, we have implemented certain log pages and certain features respectively. Yeah, and work is in progress to implement the rest of the features and commands. So this diagram gives you an overview as to how the interaction happens. So as you can see on the guest side, we have NVMe CLI, and on the host we have the QEMU MI module. So basically there will be so the communication happens between this NVMe CLI MI plugin and the QEMU MI module by the I2C interface. So what we have done is we have fixed the address so that NVMe CLI and QEMU can communicate over that address, basically the I2C address. So using this, the communication will happen. Yeah, so that's about the QEMU MI implementation. Now we'll be talking about one more feature called the administrative controller. Uh, in this, so the NVMe 1.4 spec defines mainly three types of controllers. One is IO, the other one is admin, and the last one is the discovery controller. So IO controller mainly focuses on the commands which deal with the logical block. So let's say read, write, dataset management. So these all fall under the IO controller category. So whereas the commands which which deal mostly with the management capabilities, so they fall under the administrative controller. So some, to give an example, so let's say we have get log pages. So some of the log pages under get log page and some of the features under set features or get feature. So that those can be sent by the administrative controller. But IO commands like read, write cannot be sent by administrative controller because they'll be prohibited. So as you can see, here is a depiction from the NVMe 1.4 specification as to what are the different types of controllers. So yeah, as uh, I mean, how the QEMU implements is as per the specification. So in the identify structure, so we have a controller type field. So QEMU can populate as to what type of controller it is. Is it IO controller or admin controller or a discovery controller? And based on that, the host will come to know what controller it is, and it can send appropriate commands. So also, as I mentioned earlier, so it can prohibit certain commands which are meant to be prohibited. So since IO commands are not supposed to be sent, so for example, create IO SQCQ, delete IO SQCQ, read, and all the IO commands. So these are all prohibited. Along with that, some features which deal with the logical block, features as in set features or get feature command, so which deal with the logical block. So even those are prohibited. So how do you specify a controller to be a administrative controller in QEMU? So we have defined a parameter in the launch parameter. So that is the controller type, CNTRL underscore type. So if you specify 3 there, so that means that particular controller is going to be a administrative controller. So yeah, this is all about administrative controller. Let's talk about the namespace write protect feature now. So NVMe 1.4 talks about a new feature, that new FID. So that is namespace write protection config. So this is to basically control the write protection state of a namespace. This is as part of the set features command. So the major use case of this is avoid altering of high critical data. So let's say if I have a high critical data or OS data and it should not be altered. So the host can make use of this particular feature, and it can protect that particular namespace so that accident altering of that data is avoided. Also, the specification talks about different states of namespace write protect. So that is, one is no write protect. So this is the default state in which the namespace will be present once it is created. And after that, we have a write protect state. So then we have write protect until power cycle. So write protect until power cycle is basically lasts only till power cycle. So after power cycle is applied, it will go back to the no write protect state. And we have a permanent write protect state. So basically permanent write protect is to permanent, as the name suggests. So it is to permanently write protect a namespace until it is deleted. Now let's talk about how we have implemented the power cycle feature in the QEMU. So what we have done is, since it's an emulator and there's no support for power cycle, so we have added a QMP command to issue the power cycle. So once the QMP command is sent from the guest, and let's say the namespace is in write protection until power cycle, so it will get changed to no write protect. So this is how we have emulated the power cycle feature for namespace write protect. And also, since the QEMU states are not persistent across different launches, so we have provided an option in the launch command to emulate this permanent write protect feature. So the parameter for that is called PRM underscore WR underscore protect. So if it is set to true, so then that particular namespace will be permanently write protected. And with this, we can emulate the permanent write protect feature configuration. So that's all about namespace write protect feature.
So rounding up, as you have seen, we have introduced several new features this year, and some of them have made it upstream, some have not, and we've provided those instead in the OpenMPDK repository. So these features continues to help developers test drivers and applications, and it is a lot of work. So as always, we are always looking for new contributors, and especially people who are willing to test. It's become a pretty active subsystem of QEMU, and we are seeing an increased number of contributors, so keep that up. But we'll be available for Q&A during the day, so please reach out if you have any questions or any specific feature that you would like to see in QEMU. Thank you, and have a nice conference.